Hello everyone, and welcome to Lab 12, the last lab of Math 366. And in this lab, we're going to talk about linearization. So last lab, we talked about linear systems of differential equations, and this lab, we're going to talk about nonlinear systems. But as you should have learned in class, nonlinear systems can be approximated by linear systems if the numbers are small enough, and this lab will demonstrate that for you. Alright, so starting for question 1, consider the linear systems x prime is equal to negative 3x plus root 2y, and y prime is equal to root 2x minus 2y. Part A, use p-plane with window absolute value of x is less than or equal to 0 and absolute value of y is less than or equal to 0 to plot several orbits for the system. What kind of equilibrium point does the origin seem to be, and print out your plot. So if we go into p-plane and plot this, and print out a few orbits, we should see very readily that this is a sink, right? You can see all the arrows are pointing towards the origin. So this equilibrium point at 0, 0 would be a sink. Now, for B, in the p-plane options menu, select erase all solutions and use p-plane with window absolute value of x is less than or equal to 0.1 and y is less than or equal to 0.1 to plot several orbits. Okay, so we don't actually need to do erase all solutions, we just change the values here. And graph it. And we should see that it still should be a sink. Now, for part B, notice that all of the orbits seem to be tangent to one particular line at the origin. Okay, so yes, we can see that if we plot it somewhere around here, maybe like 0.7-ish, we can see that all our solutions would be tangent to this line. And finally, for C, let A be the 2 by 2 matrix for the system, and as in Lab 11, use the command BD is equal to eiga to find the eigenvalues and corresponding eigenvectors for A. Use this information to prove that the behavior you observed in A is correct, and how does a line noted in B relate to the eigenvectors of A. Okay, so again, we go into MATLAB, type A is equal to our matrix here, and have BD is equal to eiga. We see that B would be this matrix right here, and D would be this matrix. So our eigenvectors would be -4 and -1, and our eigenvalues would be -4 and -1, and our eigenvectors would be this column and this column. So for the first part, prove that the behavior you observed from A is correct. Well, in A, we observed that the equilibrium point is a sink, right? And if you remember from Lab 11, if it's a sink, if it's a nodal sink, then the eigenvalues should be both negative, and we see that this is true. Now for B, notice that it's a tangent line, right? All the orbits are tangent to this one particular line. Well, if you might guess that this line has a slope of about 0.7, which coincidentally is exactly this eigenvector. So if we just type this, if we do 0.5774 divided by 0.8165, we should find a value that is very close to actually 0.7. I believe it's 0.707 something. So the slope of this line is just this eigenvector. Now for question 2, we're going to consider this nonlinear system. It's very close to our old system, except the x prime term has a minus xy tacked on, and the y prime term has a plus x squared plus y squared term tacked on. Now again, the origin is an equilibrium point, and we're going to repeat parts A and B from part 1 for the system. Okay, so we're going to start off by plotting it with x is less than 10 and y is less than 10 p-plane. So if we graph it, and draw a few orbits. So at first glance, this behaves a lot differently from our original equation, right? There's all these weird shapes going on, and it's harder to predict how exactly this will look like. But if we change our bounds to 0.1 instead of 10, we will find that this system actually behaves very similarly to our linear system. Now, why would this be? Well, there's an explanation here, right? So suppose x and y are very, very small, and in our case, very small works out to be 0.1, I guess. And we expect that the terms xy and x squared plus y squared would be smaller in comparison to just x and y, right? So if we had maybe 0.1, we would see that xy is equal to 0.01, which is like an entire order of magnitude smaller. So that near 0, 0, our nonlinear system should just behave like our linear system because these nonlinear terms, minus xy plus x squared plus y squared, should be negligible. So this system is called the approximating linear system to the nonlinear system, and this matrix, is called the Jacobian matrix. Xy is equal to 0, 0 for the system, and we can also do this for other equilibrium points as well. But since our equilibrium point is at 0, 0, this is the Jacobian for this matrix. And in general, the Jacobian matrix will look like df dx, df dy, dg dx, dg dy, which should look very similar to something that you have learned in class. Alright guys, so for question 3, each of the nonlinear systems given below has an equilibrium point at the origin 0, 0. And for part A, determine the approximating linear system for each of the nonlinear systems about 0, 0. Find the eigenvalues for these linear systems and use them to predict the nature of the equilibrium point at the origin for A and B. Okay, so what I'm going to do is do it for equations A, and that should give you enough of an outline to do B by yourself. So here we have our system A right here, and if you recall, our Jacobian is just df dx df dy dg dx dg dy, right? And so x prime is going to be f, and then y prime is going to be g. So our Jacobian here, oh right, this has to be evaluated at 0, 0, which is our equilibrium point. So let's see here. If we take the partial with respect to x of x prime, we get minus 2, minus 3x squared, minus 2xy. Okay, df dy is going to be minus 1, minus x squared. Okay, and dg dx, partial with respect to x of y prime, is going to be 1 plus 2xy, and partial with respect to y is going to be minus 1 plus x squared plus 3y squared. And all evaluated at 0, 0, so if we plug in 0 for both x and y, we get minus 2, minus 1, 1, minus 1. And so our equivalent linear system is just going to be x prime is equal to minus 2x minus y. Y prime is going to be x minus y. And you should notice that if we had just taken the linear terms from our original nonlinear differential equation, we would have gotten exactly the same answer, right? Our nonlinear terms here are minus 2x minus y and x minus y. So this would work, of course, if x prime and y prime are just simple polynomials, right? But if they're more complex, like cosine xy or some weird function, you would actually have to go through the Jacobian to find this. Okay, so now find the eigenvalues for these linear systems and use them to predict the nature of the equilibrium point at the origin. So again, we're just going to use MATLAB. Again, here you can see that we have our matrix here, -2, -1, 1, -1, and we're going to find the eigenvalues and eigenvectors. Okay, so we can see that our eigenvectors are negative, or are these two numbers, I guess. Yeah, -1.5 and then plus 0.866i, -1.5 minus 0.866i. And so we can see that because both of these are not real and they're not exactly imaginary, we can probably expect this to be spirals, right? And since the real part is going to be negative, we can probably expect these to be spiral sinks. Now for part B. Plot some orbits for the approximating linear system to support what you said in A is correct, and turn the plots. Okay, so again, we're going to go to p-plane. Here again is our approximating linear system with our very small x and very small y. So graphing these, we do indeed see that they are spiral sinks. So our prediction was correct based on our eigenvalues. And finally, for C, plot some orbits for each of the nonlinear systems to show that your predictions from A also apply to the nonlinear system, and turn the plots. Okay, so again, remember, right, small x, small y. Our nonlinear system is minus 2x minus y minus x cubed minus x squared y. And for y, we have x minus y plus x squared y plus y cubed. We graph this phase plane. We should see that our predictions of it being a spiral sink also apply to this nonlinear system. Alright, now of course, for number 4, a system can have an equilibrium solution that is not at the origin. For example, consider the nonlinear system B, right? It's easy to check that 0.5 is another equilibrium point, and you can see that if you plug 0.5 and 0.5 in, you will see exactly that. So the constant functions x equals 0.5 and y equals 0.5 are also solutions to B. So to study solutions near the new equilibrium point, we can introduce u equals x minus 0.5 and v equals y minus 0.5. And substituting it in, you will see that we get basically a new system of differential equations, B star, let's just say. So now the solutions x equals 0.5 and y equals 0.5 correspond to u equals 0 and v equals 0 for B star. And this means that we can just use a Jacobian directly. It's a lot easier to calculate because we could just substitute in 0, 0 instead of doing this whole deal up here. So A. Use p-plane to plot several orbits for solutions to B in the xy plane, and find the approximating linear system of B star around 0, 0, and plot several orbits for this linear approximation in the UV plane, and show that when a small enough scale is used, the UV plot around the origin looks very similar to the XY plot around 0.5, 0.5, and turn your plots. So let's start with our original linear equations, system of differential equations, B. So here we can see this right here, and we're going to use the constraints from x and y from 0 to 1, because 0.5 is in between there. So if we graph this, we can see that our point right here, 0.5, 0.5, seems to be a nodal sink. Okay, so let's just change our bounds to 0.4 and 0.6, just to get a bit closer. And you can see this looks like a lot closer to a normal linear system. Now, for the approximating linear system of B star, remember that we'll just use our little trick here, right? So u prime is equal to negative 0.5u minus 0.5v, and discard the nonlinear terms. And v prime is equal to 0.25u minus 0.5v, discard the nonlinear terms. And so this right here should just be our approximating linear system. So then, plotting our approximating linear system, so we're just going to keep using x and y because then I don't need to change the variables. Minus 0.5x minus 0.5y minus 0.25x minus 0.5y. And going with our small bounds again, 0.1, negative 0.1 to 0.1. We should see that this linear approximation does indeed look very similar to our linear approximation earlier on, when we zoomed in around 0.5, 0.5. Right? Okay, now for part B, use MATLAB to find the eigenvalues and corresponding eigenvectors of our approximating linear system of B star around 0, 0. Then, using the general solution of the system, prove that the origin is a sink. Alright, so again, we have our matrix here, A, and we will have B, D is equal to the eigenvalues and eigenvectors of A. So, as you can see, we have our eigenvalues of minus 0.1464 and minus 0.8536. And again, since they're both negative, then our origin for this system is indeed a sink. And finally, for number 5, our examples so far seem to indicate that the solutions to a nonlinear system always behave very much like those of the corresponding linear system as long as we stay near the equilibrium point. This is not always true. For example, consider the nonlinear system below. X prime is equal to negative y minus seed. The seed for this lab is going to be 13. So x prime minus y minus 13x cubed, and y prime is equal to x. Now for A, let x and y be solutions to the linear approximation of C, then they satisfy this linear system D, and you can see that if we just take the linear terms in C, they match up. So plot a few orbits of the corresponding linear approximation, and they should appear to be circles around the origin and prove that they really are circular. So first, let's just plot a few orbits. We have x equals negative y, and y equals x, and I guess we can keep our bounds as is for now. And yes, you can see that p-plane is telling us that possible orbits, closed orbits are detected, which means that they really are circular. Now, how do we prove that they really are circular? Note that x squared plus y squared prime is equal to 2xx prime plus 2yy prime because of the chain rule here. And then use the system D to show that the expression E is 0. So we have it here, right? This is our system, and we have that x squared plus y squared prime is equal to 2x x prime plus 2y y prime. So we show that the expression E is 0. Well, we just substitute in x and y. So we know that x prime is equal to negative y, so negative 2xy. And we know that y prime is equal to x, so plus 2yx. And this does indeed equal 0. So how does it follow that the orbits of the system D are circles? Well, what does this represent, right? X squared plus y squared, this represents like distance, right? Or, yeah, absolute distance from the origin. Right? And so the derivative of the distance to the origin, or the change in distance from the origin, always stays constant, right? This means that it's equidistant from the origin, and we know that that means that it is a circle. Now, part B. Use p-plane to plot some orbits of the system C over the intervals x is less than 2 and y is less than 2. Okay, so remember our system C is right here. So now we have minus 13x cubed, and we're going to plot it from minus 2 to 2. Okay. So those are some systems. So the orbits should seem to spiral in toward the origin, but with a blank spot near the origin. Okay, yeah. So if you see right here, there does seem to be a small blank spot, right? So for C, we're going to look at it more closely, change to a smaller scale in p-plane. So we're going to be doing x is less than 0.0002 and y is less than 0.0002. So we're going to replot this 0.0002, 0.0002, so on. This is going very slowly. Okay. Shouldn't be going that slowly. Here, let me change the computation window a little bit. I guess my computer just refuses to plot all the way. It's very strange. But you should still see that they're roughly circular-like, right? Like, you can imagine that if they extended out all the way around, they would be a circle. So that's what you should be seeing. So near the origin, the orbits should appear to be loops. I know that my computer didn't show that, but they should be perfect circles. But this isn't what is supposed to be happening, right? So use C to prove that xt and yt are solutions to system C, then we should have that the orbits should move constantly towards the origin, right? So if we apply this same concept, right, x squared plus y squared prime is equal to 2xx prime plus 2yy prime, right? If we apply this to our nonlinear system instead, we should see instead that 2x minus y minus 13x cubed plus 2yx, which cancels out to be about negative 26x to the fourth. So why do the orbits move constantly to origin? Remember that x squared plus y squared is like the distance from the origin, right? So if the distance's derivative is negative, as it is here, right, this will always be negative. X to the fourth will always be 0 or positive, so this means that the distance is always decreasing, which means that the solutions will always like go smaller and smaller and smaller. But this means that our computer output is wrong, right? Our computer output, we saw that really, really close to the origin, we saw that they were like perfect circles, even though they shouldn't have been. So this might seem weird, but this is just because that computers can't store numbers this small, right? If you think about it, we were at like 0.0002, and if we took that to the fourth, that would be, I believe, like 1.6 times 10 to the negative 11. This is a very small number, and a p-plane just can't compute that. So if you remember back to our lab on numerical approximation, sometimes our numerical approximations can be wrong when the numbers get too large. Well, this is an example of a case where the numerical approximation can be wrong if the numbers are too small, right? The computer just can't deal with these numbers, so we just get um, like a circle-like thing because this basically, our computer thinks it's like 0. So we still get a circle. We get a circle even though it's supposed to be spiraling in. And finally, for part D, from the equation in C, you prove that every non-equilibrium orbit moves constantly towards the origin, right? Remember that the distance prime is equal to minus 26x to the fourth. However, their graphs and p-planes seem to indicate that they do not approach the origin, but instead each orbit seems to approach a circle of finite radius, right? So if we use p-plane to plot the specific orbit, which starts at x equals 0, y equals negative 0.2, then use these intervals, right? So we're going to change our intervals up a little bit. X is less than 0.3, y is less than 0.3. And use the zoom in feature several times near the origin to approximate that radius. If I can find keyboard input, we're going to have x equals 0, y equals negative 0.2, and solve. And you should see that it just stops at a circle, right? And this means that the number got too small, the computer just thinks it's 0 now, and just going to go around and around, and it doesn't spiral any further. So we're going to use a zoom in tool. We're going to select the rectangle. It's just easier this way. Hold down shift and select this rectangle right here. So you should see that this circle's radius is like about, if we look here, maybe like negative 0.018 or 0.018. So our radius 0.018, right? And this would seem to indicate that at 0.018 or x or y equals 0.018, our numbers get too small and the computer effectively thinks that this is 0. So in the end, we see that our approximation D are circles, but our actual differential system of differential equations is a spiral, and so they don't match up, even though the linear approximation usually does match up. And usually this happens for this specific case, right, where our linear system is a spiral, but then our linear approximation is a circle. That's just how it usually ends up not equaling each other. But other than that, that should be the end of Lab 12, and I believe our last lab. Remember to turn this in next week, and good luck.